Okay, morning everyone who's joined us just now. So we're just gonna get cracking, and then just one question. If you got any questions or while doing the session, I've got my colleague Cheryl who might keep an eye on it, and because it's a little bit difficult to look at the questions and while I'm presenting, so we'll see how it goes. But we'll just get cracking. So basically the idea of this presentation is to give you an overview of what Fusion simulation is all about. As many of the customers are already using some form of FEA, whether it's inside Inventor in the form of Inventor Professional or Nastra and FEA, Fusion simulation is probably not used that much, not necessarily because everybody is used to Inventor and the familiar interface. But the good news is that everybody has got access to all this as part of their collection suite. Now, the difference between the Fusion simulation and the Inventor simulation is that inside Inventor you have the ability to do linear and modal analysis. If you want to do something like thermal or buckling or drop testing, then either you will need to go into Fusion simulation or into Nastran. In CAD, it's now called Inventor Nastran, which you also have access to, which works inside the familiar Inventor interface. The big difference with Fusion simulation is that if you want to run a linear analysis that applies to static stress analysis and modal analysis, then you can run locally on the cloud, which means that it doesn't cost you any credits. If you want to run it on the cloud, then it costs you 5 cloud credits, and I'll show you how it actually prompts you if you want to go ahead. So you have that choice. Now, if you want to run nonlinear or drop testing, is another phrase of actually looking at nonlinear stuff, then it is 25 cloud credits, and that in that situation you don't have any choice to run it on the local PC. So, and 1 cloud credit is approximately £1, and you can buy these in packs of 100 and thousands. Okay. So the example we're going to have a look at is, if you joined us 2 weeks ago, we did an example on generative design. This is the part which was generated. Once it basically you download the actual product, it does go through FE in the background as it's going to go through the generative process. We're going to actually do a validation on this part to go through simulation again using Fusion simulation. And then we're going to have a look at a second part, which is primarily a small assembly, and this is basically a part of a motor racing car, and we've got the prop shaft, and we're going to be interested in looking at the yoke example here, and it will give you an overview of what the Fusion simulation is. We're only going to cover the linear analysis, even though it has other analysis capabilities in there as well. Okay, let's just dive in. Okay, so this is the first example, and you can see it's not a normal design. It's basically, it's all surfaces. It's an organic shape which has been downloaded as a generative design, and we're basically going to go through the validation using a Fusion simulation. Now, obviously, you might be familiar with the interface to some degree if you've been attending our previous webinars, but inside Fusion, it's basically not just a CAD software. It goes through CAD, rendering, animation, simulation, and obviously manufacturing as well. But we're going to go straight into simulation. And the first thing you're going to see is what type of analysis would you like to perform. Now, inside simulation, you can see static stress analysis, modal frequencies. These two you can actually do inside Inventor FEA, and the rest, thermal, nonlinear, buckling, and even shape generation. So this shape optimization is slightly different to generative design in that you have to start off with a basic shape, whereas with generative design you can actually start off with nothing and it just creates a shape for you. The one thing I like about Fusion simulation is that you have the ability to simplify parts. Now, in this example here, we're not going to do any simplification. We're going to try and do the analysis on the actual product design. Okay, so we just go through a create study. Just gonna okay. Right, so once we're inside the simulation environment, we are basically ready to sort of apply the boundary conditions of the materials, and typically the materials have already been assigned. The first thing we're going to do here is, if you want to simplify it, so for example in this one is not easy to simplify, we could put fillets, we can remove fillets and chamfers, for example this one here, but we'll leave them as they are for the time being. The materials will probably already be assigned, so if I click on this little material here, you can see the material has come across from the download or from the Fusion part environment. And the properties are also assigned. If I pick on the material, you can see it's populated with the correct material properties. So what we're going to do now is try to fix it down, about how it's going to be fixed in reality. So let's just get the orientation correctly. And we have structural constraints. You can apply bolts inside Fusion as well, and then you can have some special connectors as well in here. So we'll go into structural constraints. And we're simply going to tie these down as if they're going to be restrained by the bolts. Okay. Okay. So you can see padlocks on all the faces which have been restrained, and now we're ready to apply the force, similar to the one we applied 2 weeks ago in the generative design example. So we're going to loads, and okay, and again you have similar types of loads in the generative design example, but you also got 2 extra ones, remote force and hydrostatic pressure. But we use the same one we used in the previous example. And then I'll use the vector components in the Y direction. This is based on the global coordinate system. Okay. And then just before I start to define the mesh, we're simply going to apply another load case. I think okay, let me just delete that one. I was meant to clone it, not create a new one. That's the one I was meant to use. And then it copies the load as well, so we're simply going to modify that and go in the Z direction. Okay, so we've got 2 load cases, so by highlighting it, so we can see here load case 1 and load case 2. Now we can ready to create the mesh, so we go into here and we'll just click on yes, and that will generate the mesh for it to sort of get ready to analyze. Now obviously while it's doing that in the background, we can actually specify local mesh control. What that basically means is that we can apply a mesh in areas of interest and make them finer in that area. We can control how the mesh grows from a fine mesh to a coarse mesh. So we have all that abilities inside Fusion, and I'll show you that briefly in the assembly example. Now you can see here in the background the example is very detailed, and one of the things I like about Fusion that its mesher is very, very robust. I will not say that it will mesh anything, but it's not, I won't be far off. Okay, once you've defined all that, we can basically do a pre-check, and that pre-check would simply give us an indication visually if anything is wrong with the part or something is missing. So we're okay in this case. And once I click on the solve, I'm not going to click on solve, but you can see there I have the ability to well, at the moment it's on the cloud, so it's going to cost you 5 cloud credits. But if I click on locally, it will basically require no cloud credits to be able to run the analysis. So I'm not. So what I'm going to do here is I'm just going to close this down, and we'll open a file with the results already. And here we go. So what you see here is the displacement results for load case 1. In this example here, I've got an extra load case, so you can flick between the load cases, and you can see there are slightly different displacements. You can also have a look at some stress results. Okay, you can't see a great deal here, so let's just try something different. Okay, and what we can do, you can see here, I'm just left clicking my mouse button on the actual legend, and you can change the scales or the divisions, but you hardly can't see anything. So I'm going to change the legend from smooth to banded. And then if I move my legend, you can see, and this I think is pretty cool. That is probably impossible to do it like this. You have to go and click on the legend color inside Inventor or even Nastran and basically change the divisions, have a look. You're not happy with it, keep on doing it. But here you can dynamically change the look and feel how you want to see the results. And this applies to stress, displacements, and then also you can have a look at the safety factor. The safety factor here is very high. It's in excess of 15. And just to give you an idea, if I just go into here and click on that, you can see it's very, very high. If that was below 15, then you probably see it on the legend bar. Now, one of the other cool things I like about Fusion is that, okay, I'm flicking between the load cases. What I can also do here is I can compare the results. So if I just have a look at, let's have a look at stresses. If I change that back to, cancel that. Okay, so we look at stress results. And what you see here on the screen here on the left hand side, I've got load case 1, and on the right hand side I've got load case 3. Now at the moment, if I just minimize that there so it's a bit clearer to see, you can see two different type of load case results in the same sort of view orientations, and then you can compare how the loading is affecting the actual part itself. Now if you want to flick between a different result, let's perhaps stress, then it basically updates both of them. You can see here on the, if I move it away from the screen, you can see here on the left hand side we've got a maximum stress of 58, and the right hand side we've got 81.5, and you can basically look at probes if you want as well in there. But if you zoom into the area of interest, it's probably going to be where it's restrained. You can see here on the left hand side we've got some hot spots. If I turn it around, there you can see it there. And I think this is pretty cool, how you can compare results between two different load cases, different boundary, or even different materials. Okay, so let's have a look at an assembly analysis. So that's just giving you a brief overview of what you would typically do once you download a generative design part. Even though it's been through the simulation in the background, you can validate the designs again, and clearly the example shows we have a very, very high safety factor. Okay, so right, let's look at. So what we've got here is a two-part assembly. So this presentation can relate to a 2-part or a 50-part. The process is exactly the same. So we go straight into simulation environment. Okay, that was loud. So if I just go into static stress. Okay. So far, the process is similar. Now, you could basically go into simplify, and we could remove these. Let's just try that then very quickly. So if I go into the simplify mode, let's just remove faces. Let's remove that one. And I think we should have similar ones on the other side. Okay, they do that one. Let's try something else, because I need to connect the connecting faces. Let's try Let me try one of these fillets here. Okay, it's fine, just fillet. Now what I did there is, rather than trying to pick the fillets one at a go, I'm simply gonna pick on remove features, and I've just picked that part. This is the part I'm not actually interested in. I'm more interested in the other part, because I had to create this slave part to be able to apply the moment load. So I just want to show you how the simplify mode actually works. So I'm not sure how long this is going to take, but let's just click on delete on here. Okay, that was super quick. Now you can see here it's basically removed the fillets on that part. Now this is within the simulation environment. If I was to go back into the Fusion part and assembly environment, the fillets will reappear. This simplification process only stays within the simulation environment. Okay, so once I'm happy with that, we're back in the simulation environment. I mean, this would actually help to reduce the meshes. So it does have its benefits. In the materials that are already been predefined, the next thing we're going to do here is apply constraints. Now typically I would actually pick one face of the teeth and go all the way around, but to just sort of make the process a little bit quicker, I'm simply going to click the cylindrical face here, and then we're going to apply a load on the other part, and it's going to be a moment load on this face here. This is the reason why we had to create this dummy part, and it's newtons millimeters, and now I'm going to specify values in newtons meter. And if I click on the load again, you'll see that it has converted to millimeters. Okay, now once we've done that, now we can start creating the mesh on here. So if I click on the mesh toggle here, now that was pretty quick. You probably didn't see something, but when it was doing that, because it's an assembly, I did not create contacts. When you click on the mesh, it automatically creates contacts, and the default contact types are bonded. Okay, and you can see the mesh is pretty coarse around here. Now what typically happens here, now I've done this once or twice before, and the high stresses are going to be around here. So what you would normally do, rather than creating a refined mesh across the whole body, it makes sense to refine the mesh in the area of interest. If I'm just going to click on edit here, and you can see this is the advanced settings, and at the moment you can see here it's a pretty coarse mesh. So if I drop that down to a lower value, and you can change the how it grows. At the moment that value there, this one here is 1.5. What that basically means is that how it controls going from a fine mesh to coarse mesh. At 1.5, that is growing at 50% rate. If I drop that down to, let's say, 1.2, that's about 1.1, then that will grow from 10% from a fine mesh to the coarse mesh. So it grows gradually. So if I press OK on that, and before I generate the mesh, we're going to do a local mesh control on here. And if I just go down here, you can see it. There's local mesh control. If I click on that, and if I pick that face there, even that, and if I drop the slider down towards a smaller number, you'll see that it was too much actually, that one. Okay, let's press OK on that one. Now, if this, I have already done this on a different mesh, so if I just right hand click on here, generate mesh, we'll see how long it takes. If it takes too long, we'll just move on to the other example where I can show you how the mesh has been generated. And the one thing to note in Fusion is that I don't know if you've actually tried looking at a a section view on your results, and you may have noticed that if you create a section view using the Inventor commands inside Inventor and then look at results, you probably realize that your results are all gone hollow. The reason for that is Inventor FE, as an example, does not produce a volume mesh. It only creates a surface mesh. That doesn't mean the results are wrong. Mathematically, the results are correct, but visually you cannot see the stresses inside the thickness. And I'll show you an example in Fusion how to do a section view, and you can actually look at results inside the actual part itself. Now you can see here straight away that we've got a finite mesh and how it grows from a fine mesh to the rest of the body itself. Okay, so now once you've done that, if I just click on this little button here, degrees of freedom view, you can see it's fully fixed. I did not specify contacts, but it did it in the background when I created the mesh. So what we'll do here, well, let's try something here. Let's have a look at what contacts it created. It's created bonded contacts, but in reality, they are not bonded. They're probably going to have some, they probably can't they can slide, but they may be able to separate. So let's try something different here. If I move these, suggest rough. Rough is basically, it can't slide, but they'll be able to separate. So if I just use a different type of contacts, I'm going to show you something here that when I click on degrees of freedom, you can see here the green item is fully fixed and the blue one is potentially fixed. That will still run, but if I was to then close that one and change the contacts again to something different, let's make them separation so they can slide out. And let's try again. You can see that will definitely not run because you have to have them fully fixed or potentially fixed to be able to get a successful analysis. So just be careful on the contacts. So now let's go into the results. Okay. So now we're going to go to the simulation environment and let's have a look at the results. Now what I've done here is I'm simply going to bring the other part back again. Even though we're not interested in the slave, we just want to, so let's look at safety factor. Now when I look at the safety factor results, it's telling me the assembly is not good enough. You can see down at the bottom here, it's got a 0.5 safety factor. So that doesn't sound good, but when I actually look at the minimum it's in the other component, which I do not really care about. That component was created to be able to apply the load. So if I hide that like it was already hidden, you can see now it's above 1. Now this is for a racing car, and in the motorsport industry, they tend to work to a safety factor of as long as it's above 1, it's fine because it'll last a season. That's how it works. So I'm happy with that. So just be careful when the safety factor comes up. Now what we can do here is let's have a look at the stress results, and you can see here the maximum stress is actually on the fillet, which we had anticipated, hence the reason for refining the mesh on the actual fillet itself. So what we can do here is I can display the mesh, so you can see it here. And the other thing I like about here is obviously, if I just spin it around slightly, I'm going to hide the probes for a moment. And the other thing we can do here is, as a sanity check, because we applied 2000 Newton meter, the reaction on my restraint should be almost identical to that. So the way we can check the reactions is to go down here, click on reactions, pick on the surface where the restraint was applied, and you can see here it's almost 2000 Newton millimeter. And this is a pretty good way to check whether the loading was applied correctly. Now the other thing you can do here is look at surface probes, just like Inventor. So what you're doing here is I'm simply dragging the mouse over the body, and if I just click here, that probe itself is on that location on the surface of the model, and this is very similar to Inventor. Now, but what you can also do inside Fusion is you can pick a key point. You may have some notches or holes inside the actual thickness of the body to determine the stress. So if it's called create point probe. So let me pick up a reference surface. Let's pick it here so we know it's going to start. Let's just change the orientation slightly. If I move it in about here, it's still inside the model. And I think that is pretty cool. You can actually look at the stresses inside the actual thickness, unlike Inventor as an example. And this is ideal for very detailed components with a lot of features in there, with holes, notches, fillets, chamfers, or cutout. And the other big thing in here is, if I just let me delete all the probes, is to do a slice plane. Now this is pretty interesting because everything here is more or less circular, so I'm just going to look for a flat surface somewhere at the top. Just click here. Just drop it right down to the middle somewhere, and then something like that. Okay. And there you go. And you can basically look at the thickness in here. You can actually change the style, look at mesh lines, and that they don't pretty because it's 3D mesh. So I'm just going to hide these, pick that one. And then if you want to hide the plane itself, it's down here somewhere, I think. And there you got your section view. And you should be able to still, I've not tried it, but let's try it now. Create a point probe. You can actually pick on the surface there. There we go. Okay, so I think that, so it gives you, and you can also look at, if I just hide that one again, and there's other commands in here. So if I hide, delete all probes, you've got your deformation scales. Let me just delete that. Okay, you can look at deformations and you can increase it. You can play animations in here. But what I'm going to show you here is the compare. Same thing again like we did before with assemblies. And look at the height. And now that's what's that one? That's lowercase 1, and that's lowercase 2. So we can see here with the same sort of scale, that produces higher stresses. And if I change that to safety factor, you can actually see it. The one on the right hand side is just slightly above 1, and the left hand side is, as before, 1.575. Okay. Okay, there's a lot more in there now, but obviously just want to give you a very, very quick overview of what it's all about. So I think we're just ready for any questions you guys may have. And I've also got the 2 other webinars we have coming up in 2 weeks' times from my colleague Cheryl. The first one is on render, and the last one is on manufacturing. So I'm just going to be on standby for the next 5 minutes or so to answer any questions or queries you may have. One question I have is that if we don't have collections, how can we have a monthly subscription on Fusion? And the answer to that is yes. It's not Fusion Ultimate or Fusion Basic, it's just called Fusion 360 now. And that includes everything. Another question I have here is, will it do thermal and stress analysis together? And the answer to that is yes. And the third question here is, will it do elastic plastic analysis, and can we define our own curves? And again, the answer is yes. Okay, now if you have any further questions offline, there's my details. You are more than welcome to send me questions afterwards, and I will try my best to answer them. I would like to thank everybody for their time this morning. It's appreciated, and maybe might talk to some of you hopefully in 2 weeks' time. Thank you very much, guys.